I promised you all in lesson 1 that we would be doing these similarity transformations, that we would need to know a lot of our unit 3 work with our rigid motions. But these are no longer going to be rigid motions. There will be rigid motions composed with the dilations, just like we dilated last time, either enlarging or shrinking, reducing these figures, and then performing some sort of rigid motion after we've done a dilation. Or maybe we'll do a rigid motion first and then a dilation. So we need to review a little bit of our rigid motions, and then we're going to use that information to determine if these figures are similar. If we can show that there is a dilation and a rigid motion that orients one over to the other, and we can show that the sides are proportional, that the angles are congruent, then we will have similar figures. So we'll have to review a little bit about these rigid motions, knowing how to write reflection rules and read them, knowing how to write translation rules and read them, knowing how to write rotation rules and read them, and know how to do those compositions. Remember, we do the inside out. We might have it as the dilation of the translation of the reflection, and then have to work that backwards. So we would reflect and then translate and then dilate, depending on the order in which they're written, but we do it from the inside out. We do it seemingly backwards. Our rules for rotations, again, I don't need you to memorize those. The rest of that, we should be able to translate left and right. We should be able to reflect over a horizontal and vertical line. Some of those diagonal lines, I know it was a little challenging with writing our rules and knowing what does the equation y equals x look like, or y is the opposite of x from Algebra 1. I know that kind of stuff is challenging, but horizontal and vertical lines should hopefully not be too much of a hassle. If you know that that's a struggle for you, then make sure to see your Algebra 1 teacher or come visit me, or look back over lessons 3.1, 3.2, and 3.4 from last semester, all right? Again, rotating over the x-axis is this, reflecting over the x-axis is the same as reflecting over the line y equals 0. The y-axis is the vertical line x equals 0, and all that does is change the location. So again, it just moves it to the other side. If you're reflecting over the x-axis, the x value stays in the same place, but the y value is what becomes opposite. If you're reflecting it horizontally over the vertical y-axis, the x value is going to change signs, but the y value stays the same. All right, and there again is your rotation rules. So that information might be pretty useful. When we are composing these functions, again, we want to make sure that we can read these from the inside out and be able to understand how this end result is related to our original figure, that this figure and that figure are similar to each other, meaning that there is a scale factor that I multiply all the sides by to get there. Obviously, there's some other rigid motions applying there, so we want to keep track on those. But the way that we've got this written is that we have a reflection over the line x equals -3 of the dilation by a factor of 1/2, again, about the origin is our center of dilation, of triangle ABC gives us triangle A prime, B prime, C prime, or A double prime, B double prime, C double prime. So the first step is to do the dilation. Taking this figure and dilating it by a factor of 1/2 is the compression or the shrinking, the reducing of that shape, where the x's and the y's are all multiplied by 1/2. And then we reflect it over the vertical line x equals -3. All right? So we want to be able to follow those rules, just like we did last semester, and do the dilations as we're asked to, like we've learned about doing the dilations last class meeting. All right? I know that that's going to be a struggle. I know that we're going to wrestle with that a little bit. So, oops, my stuff didn't pop up as it was supposed to, but that's okay. Here we have x is at 3, 5. This is going to take us some time, obviously. X is at 3, 5. So 1, 2, 3, 1, 2, 3, 4, 5. This is where x is. -1, 4. This is where y is. And then 1, 7 is where z is. So this is our original pre-image, right? This is our original triangle x, y, z. I'll do my best to draw those as well as I can. And it says that this is the dilation. This is the dilation by a factor of 2 of the translation, right 1 down 2, of triangle x, y, z. So if we're doing this how we're supposed to, we'll do this first, and then we'll do the dilation second. First, and then second. All right? Inside out. The dilation of the translation of the triangle. So let's translate this back to, forward 1 and then down 2. So if I go forward 1, down 2, here is now x prime. Forward 1, down 2, there is z prime. Forward 1, down 2, there is y prime. All right, so I've moved that to these new locations. This is where x prime, z prime, y prime is. It's our translated figure. Our translated figure is just shifted over 1 and down 2. Then we need to dilate by a factor of 2. All right? Oh, here I did the translation. All right, so we found those. But now we want to dilate by a factor of 2. So I'm going to take each of these x comma y's, and I'm going to double the x's and double the y's. So if I'm doubling these, I'm going to get 8 comma 6, 0 comma 4, 4 comma 10. I just doubled each one of those. All right? And so 8 comma 6, I'll do this in a, let's do it in black. That's my last color I've got. So I've got 0 comma 4 for y double prime. I've got 8 comma 6 for x double prime. And then I've got 4 comma 10 for z double prime. All right? And so this figure is translated and dilated. Translated first, dilated second, and it gives us this new drawing of triangle XYZ, that is x double prime, y double prime, z double prime. All right, the question is which parts of that made sense and which parts were a struggle. Be ready to ask questions on that, but I also want for you to try one. Here we have a rotation of XYZ, same XYZ, all right, original, but we're gonna rotate that 90 degrees, use our rules, our rotation rules, and then dilate by a factor of 1/2. So there's your reminders. You should have that on your notes anyway, so you don't need to put that up there, but that'll be there for when I have to do this with you in class. All right, but check over that one. All right, example 2. Make a note. This is hard because you have to write the rule. You have to understand how did this get over here, all right? And so we want to be able to think through this well, and we want to make sure that we can start here and end there. Number 1, I want for us to recognize that we have a 180 degrees rotation, and then it appears that we have a dilation. Now, if I want to figure out what my k value is, what my dilation is, I can see that my new figure is 4 units long, whereas here it's 2 units long. So I can find out that my k value is equal to 4 over 2, which is going to give me 2. I can find that using those horizontals. These diagonals, it's a lot harder when they're diagonals. We would have to use the distance formula, all right? Where we had x2 minus x1 squared plus y2 minus y1 squared, and then we took the square root. No one wants to do that, all right? So if we have a horizontal, we want to try to use the horizontal. If we don't have the horizontal, then we're going to have to use the distance formula. But hopefully you can tell this was over 1, up 3, this is over 1, down 3, over 1, down 3, and so you can tell that it happened twice, all right? So hopefully you can kind of either figure that out by thinking, or you can calculate it using the distance formula, or just by doing some straight up division if we have horizontals. So we know that our scale factor is going to be a factor of 2. Again, about the origin, since it's about the origin, we're not going to put the center there as O. We can, all right? That's helpful if you want to, but it is not required. But that is first, or is that second? The way that I would think of this is that we rotate this 180 degrees here and there. All right, that we rotate this 180 degrees, and then we dilate it. All right. So I would write this as a rotation 180 degrees about the origin of the dilation by a factor of 2. Actually, I would rotate first. Womp, womp, womp. Rotate first, hit it. So I would rotate first, and then I would dilate it by a factor of 2, again about the origin. You do not need this, not required, because we know that we're dilating about the origin. And we're going to do that of triangle XYZ. But then what order do I write these letters in? All right, these orders, X goes to J, all right, Y goes to K, and then Z is going all the way over to L. Okay, so that is how I would write that rule. Folks, that is tough. I don't have a good recipe for making that any easier. You may wish to look back at lessons 2 and 4 in Unit 3 to talk about how we write those rules. It does require us to think and visualize and process and maybe make educated guesses. If you make a guess and it's wrong, at least you could see it worked out that like, oh, if I use that rule to move this thing, it doesn't get me to where it needs to be. It tells you, that's just called checking your work, right? We want to make sure that we can check our work and have the correct output there. That is a little bit challenging. Oh, okay, so we have the dilation, blah, 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 I did that. All right, so similar figures. All of that, folks, is kind of tying that work to chapter 3. From here on out in this chapter, we're going to focus on kind of the algebraic computational thinking with respect to similarity. All right, so I've used that word similar, basically saying, hey, these angles are congruent and these sides are proportional. And so I've been using that phrase, but we haven't really formally defined it. So, vocabulary, similar figures. Figures are similar if they have congruent corresponding angles and proportional corresponding sides. We've talked about proportional sides already with our dilation, so that won't be a stretch. Figures that undergo some rigid motion and dilation, they are similar, all right? They are similar to each other, all right? Because their sides are going to be proportional and the angles are going to be congruent. So conversely, if we think about that in reverse, if we know figures are similar, then that means that there is a similarity transformation. We just wrote a similarity transformation on the last slide. And so we want to be able to think like, oh, this is just rotated and then it's dilated, or it's just reflected this direction and then shrunk down, or whatever. However the situation is, but that's going to require you to think about what you're seeing. All right? And again, that's hard because you're learning this, and the whole point of this class is that you're learning to think. And thinking critically about what you're seeing is hopefully the end result, all right? Whether or not you can do this in life is not the big deal, but if you can look at a situation and think about it, that's a big deal. That's what we want from you. So, for any figures A, B, and C, these properties are true. You can just write those down, all right? If A is similar to B, then B is similar to A. Transitive property of similarity. If A is similar to B and B is similar to C, then A is similar to C. Every figure is similar to itself, obviously, even though that scale factor is 1. We call that congruence, but that congruence and similarity are kind of the same thing. This notation of this little squiggle is our similarity symbol, all right? It's kind of a weird deal, but that should look familiar, like when we talk about congruence, what that little tilde is referring to, all right? And so here we are painting the picture of where that tilde with that equal sign comes into play in congruence. The tilde here means is similar to, all right? So write those down and we can converse about that more as needed. So the question is, are these figures similar? And if so, describe their similarity transformation, all right? If you can write the similarity statement, do that. That's what we want to be able to do. And so let's chat through these. Describe a possible similarity transformation. So this to here looks like it's been rotated maybe 270 degrees. So this is a rotation. And then it is a dilation and enlargement. A dilation of a rotation is how we would classify this. And we should be able to write a similarity statement. So the similarity statement is going to be a little bit interesting, but what I would write for a similarity statement, the order of the letters matters. So triangle ABC is similar to triangle A prime, B prime, C prime. This is a similarity statement. Similarity statement is written over here. The description is what goes on in your brain. I'm actually not concerned with you writing these out usually. I do want you to write it out for letter B here. Right? But I want for you to be able to think of what's happening, all right? So this, I would consider that there is a reflection and then a dilation. So I would say that this is a reflection, I'll write this in red, a reflection and a dilation, an enlargement, all right? Oh, actually, I'm sorry. We would go from black to orange, so I did that in reverse. All right, we're gonna reflect, oh, and then we're still doing a reflection and a dilation, my bad. But this is shrinking down. A dilation that is going to be a reduction. That's a reduction. Whereas this one is an enlargement. Enlargement. So again, thinking is the K value is bigger than 1. Here the K value is between 0 and 1. Okay, so we want to think about that stuff because it would make sense. But then which parts go with which? Well, we know that this quadrilateral WXYZ is similar to W prime, X prime, Y prime, Z prime, all right? These go together, these go together, those go together, those go together. We want to be able to write our similarity statement. We're going to reflect it and then compress it, right? Reflection and dilation. Right here, rotation and then dilation, make it larger. Thinking through that critically, again, is part of the process here. If you're just writing the things down, you're not engaged in what I'm explaining, it's going to make it hard for you to do this thinking when you're asked to do this thinking on your own. All right, so do that thinking, predict what things are going to look like so that you are able to replicate it when it's your turn. All right, so hopefully you are able to determine whether figures are similar, identify the similarity rules, the similarity transformations, and of course, being able to write the similarity statements.